all. So today we will just discuss about reversible computing and universal quantum logic gates and circuits. Yeah. Okay. So today's objective will be just okay. What is the need? Okay, why we have to go for reversible computing? So what is the computing right now we are using? Okay. So right now we are using irreversible computing. Okay. So the input, okay, you are giving to the circuit and you are getting the output. From output you cannot generate input, that is irreversible operation. Okay, so whatever computer we are using, that is irreversible computer. That means from input you can get output, but from output you cannot get input. Okay, so why it is a crisis? So what is the problem? Okay, so we need output. Okay, so our job is done. So why we need to generate the input? Because we know what input we have given. So why we should regenerate the input? So what is the necessity to regenerate the input? So we not need input, we because we only giving the input, so we know the input and we are getting, we don't know the output. That's why we are doing computation. So why we need to get reversible computer to know the input again? So it is not about input, but in the reversible process too much energy is lost. Okay, that is the crisis. We will see one by one. And when the computation become more and more, then the more and more loss will be there. So that's why we are going for reversible computing. And what are the limitations, thermodynamic limitations? Okay, and Landauer's principle, those things we will discuss. Then how to make the reversible computing possible? So what are the things to be done? Okay, then what are the architecture, what are the gates, reversible gates, and how reversibility applies in quantum. Okay, quantum inherently it is reversible. Okay, yeah. So first, so everything will starts with Moore's law. So Morse is an Intel scientist. He told that for every 18 months, the number of transistors in the chip will get doubled. Okay. For example, now I am purchasing a laptop with some performance. After 18 months, in the same cost, I can purchase double the capacity or double the performance. Okay. So that is the Moore's law. But it was it was good, and it was our trend was obeying the Moore's law. But after 2020, after 2000, so this law is broken. Okay, that means you cannot keep on increasing. Okay, there is a limitation. So what is the limitation? The chip size. Okay, the chip size is the limitation, transistor size is the limitation. So they keep on reducing from millimeter to nanometer. Okay, now we are in the 2 nanometer transistor size. So beyond that, okay, the voltage leaking, current leaking, these things are happening. So the Moore's law ended here. Okay, when the Moore's law ended, that time we went for multi-core architecture. So earlier in software engineering and other things, software companies, what they will tell, you no need to write any performance code. Just you write the code, it should execute. That's it. Performance we will get from the hardware. They will increase the clock speed, they will get the performance. They will increase the catch, they will get the performance. So they will just do whatever the changes needed in the hardware and they will get the performance. So as a software engineer, you just write a code with the logic, it should work. That's it. You no need to do anything in the code for the performance. So that was the era long back. But now it is different, because now no more you cannot increase. Have anybody have seen more than 3 gigahertz processor? 3.2, 3.5. So it stopped. Okay, so after 3.5 it stopped, I guess. So why it stopped? Because after 3.5, if you just increase the clock speed and get the performance, it will heat the chip. Okay, so the multi-core things came. Okay, so multi-core things came. So now also it is even now with multi-core also many things is not possible. So we are going for the quantum and other things. So performance now constrained by heat, not transistor count. Okay, so heat is a main limitation, not the number of transistors. You can pack. There are a lot of sophisticated technologies there. We can pack more number of transistor in a small die area also. That is not an issue, but temperature is an issue. Okay. So as all of you know, now more AI, more HPC, more quantum, these things, quantum simulation. So the number of GPUs are increasing. And GPU actually it's a many core architecture. CPU it's a multi core architecture. GPU is a many core architecture. There will be thousands of cores and the size will be very less. So the heat will be again problem and energy. It consumes more energy, electricity. Okay, and the amount of electricity it consumes, all electricity is not converted into a useful work. 80% of the energy is dissipated as a heat. Only 20% of the electrical energy is converted into the useful work. So that is the main challenge here. Okay. So 80% of the energy is consumed as a heat only. So what is the problem? So heat is the main problem for, if you do more computation, more heat will generate. And more heat, more power dissipation, so more CO2 emission, everything. Okay, linked. So power demand is growing, so more and more data centers are coming up. So now also India, Microsoft has invested 1000 crore for data center in Vizag. So more and more data centers are coming up. Adani is investing in data center. So now everything is going into the data center, edge data center. So too much power demand is there for IT. Okay, and many AI model training, inferencing. So too much power demand is there for data center and HPC AI tasks. Okay. Okay. So there is a law of thermodynamics, second law of thermodynamics, okay, which states that in a closed system, entropy never decrease. Entropy is a disorderness. So disorderness, for example, if you consider like a big boss kind of shows in TV shows. So initially there will be some contestants, 10 or 20. So they will be in one home. Initially they will be good. The relation will be very cordial. Everything will go nicely. But over time they will be fighting with each other. So that means the entropy is increasing. So that is the Maxwell's, that is the second law. What it says, entropy in the closed system will never decrease. Over time it will increase. Okay, the disorderness will always increase. If you put some 10 people in a room, okay, first day there will be some good relationship, but or in the 10th day or 100th day they will be fighting with each other. That means the entropy is increasing. So that is second law of thermodynamics. Second law of thermodynamics says that entropy in a closed system never decrease, it will always increase over time. That is the second law of thermodynamics. But the Maxwell, okay, what he did a thought experiment. He wanted to disprove, okay, he wanted not disprove, he is telling that Maxwell questions this law could be bypassed on a microscopic level. Okay, if you go in the smaller scale, this law may not work. That was his experiment. Okay, that was his thought experiment. He did not do with any equipment. It's a that's a simply a thought experiment. Okay, in 1867 he did this thought experiment. So what he is doing, so here there is a partition, here there is a partition. So these blue dots are the cold atoms, these red dots are the hot atoms. Okay, so here there is a door, here there is a wall with a door. Okay, and this door is tied with a rope, and this rope is handled by this demon. Okay, so the demon just open only to allow hot or cold, anyone. Okay, so in this scenario it is allowing only the hot atom to go to this second partition B. So whenever hot atoms is coming, it is opening, so the hot atoms goes here and cold atom stays here. Over time all the cold atoms are in the A box and all the hot atoms are in the B box. That means here entropy is reduced. Over time in the closed system entropy is reduced, he is arguing. Okay, so the demon sort molecule without doing work, he is telling the without doing work. So just opening closing, so opening closing. So he wanted to disprove second law of thermodynamics for microscopic scale through a thought experiment. Okay, so he did this in 1867. Okay, then another scientist called Landauers, he told no, the Maxwell's things is not correct. Okay, the demon knows the information. Okay, so which is the particle okay, whether it is a hot atom or cold atom, and what is its velocity, what is its position. So all this information demons knows. That's why it is able to open the door and close the door. Okay. So without the position and velocity, how the demon can open the door and close the door? That was his argument. Then he told, okay, so demon has this knowledge of position and velocity of each atom, and okay, after the first atom passes for the second atom, so it is erasing the first information, and again it is getting the information of the second particles position and velocity, and again it is erasing, it goes for next particle, like that. Okay. So in that way, so demon is always having some information and it is erasing the information. So if it is erasing information, that means for one bit erasure there is some definite amount of energy is wasted as a heat, that he calculated. So it is, he is disproving that demon without doing work, it is not correct. Demon without doing work is not correct. Demon is doing work, that is, it has the knowledge of position and velocity, and it is erasing for the next atom to process. Okay. So this was his argument. And erasing information has a thermodynamic cost. So the demon must store information, which particle are fast, slow, that is its position and velocity. Okay. So that that formula is kt and logarithm of 2. K is a Boltzmann constant, and T is temperature in Kelvin, room temperature in Kelvin, and logarithm of 2 because it is state 2. Okay, 0 or 1. So if you erase something, so your energy is lost. So that is the minimum energy you will lose. Okay. So below that you cannot reduce. That is was his statement. Okay. That's totally, it is coming 2.8 into 10 power minus 21 joules. So for every bit erasure, for example, if you want, if you are storing some digital information, and if you want to store again the result in the same place, then you have to erase it. So one bit erasure costs this much energy, kt logarithm of 2, that is 2.8 into 10 power 21 joules. This much heat it will generate. Heat means again energy. Okay. Okay. So what is thermodynamic entropy and information entropy? So thermodynamic entropy, okay. So measures physical disorder or the number of microscopic configuration. So tides to heat, temperature, and energy flow. So second law of thermodynamics entropy is, so like big boss I told. So this is thermodynamic entropy. Information entropy is, it's like I'm humming a song. You are able to guess that song. Okay. If I sing, definitely everybody knows what song I am singing. But if I hum the song, okay, if I do humming without the lyrics, then it is difficult. But it is possible. So that is called information entropy. Okay, measures uncertainty or surprise in information or message. That is called information entropy. So this thermodynamic and information entropy is interrelated. Okay. So information, entropy, and energy, all three are interrelated. Information. If you have more information, then it is less entropy. If you have less entropy, you are going to waste less energy. Okay. So more entropy is less information, less entropy is more information. That means if you know about a person more, then the relationship will be good. That means orderness is there. So entropy is disorderness, so entropy is less. And if entropy is very less, the heat produced will be very less. Okay. So information, entropy, energy is interrelated. Any doubt? I'm not able to see the chat. Okay, okay, fine. So information, entropy, and energy are interrelated. Okay. So this Landauer's principle, okay, he told information is not logical; it is physical, because you are storing it and you are erasing it. While erasing, you have to spend minimum amount of energy as a heat or waste energy. Okay. So information is physical, he told in 1961, and he disproved thus Maxwell's demon. Okay, demo that thought experiment. Okay. So in 1961, he proposed it, then linked to the second law of thermodynamics in 2008 and 9. So these are the timeline. And entropy, angular momentum. So this entropy increases, how entropy is increases if you erase information. So first direct experiment actually published in Nature in 2012. Okay, 2012 only it is published, because it is also like thought experiment only, but practically it is proved in 2012 and further experiments. In 2014 they did several experiments in the laboratory, and in 2016 they used some laser measurements. So because what they are measuring means, so they have some information in some object. Okay, so that they are erasing. Okay, that they are erasing. So how much energy is wasted? That, because Landauer's, he told, it is kt logarithm of n. K is the Boltzmann constant, T is the temperature in Kelvin, that is around 300 Kelvin, room temperature in Kelvin, and then logarithm of 2. Okay, so that 2.9 into 10 power minus 21 joules. So they are verifying, okay, how, whether it is correct or not. So through laser probe, a lot of methods they are using to verify it. Okay, so these are some of the three experiment they did: optical trap, nanomagnet, and quantum spin. So this works for even quantum and classical. This Landauer's principles, actually it is true for classical computing also, it is true for quantum computing also. So the last experiment, quantum spin, actually it proves that they did in NMR, nuclear magnetic resonator. So here also it worked. Okay, this same experiment worked and they proved it. So how much how much energy is lost when you are erasing the information? That was the experiment. Okay, so nanomagnet they used. Okay, so north pole 0, south pole 1, so like the energy dissipate during bit reset. So while you are resetting 0 to 1 and 1 to 0, what is the energy dissipate, that they are measuring and they are verifying with the Landauer's limit. That is called Landauer's limit. Okay, so quasi state slow process. So if you just reset immediately, if you measure, the heat will be more. So what they did quasi static slow process. So they did all the experiment as a quasi static slow process. So nearly reversible but minimum heat. So it's not completely reversible. Completely reversible means there is absolutely zero loss in the process, but nearly reversible they got. And so that minimum heat, that is the Landauer's limit, 2.8 into 10 power 20 minus 21 joules. Okay, that much heat is generated. These are the experiment to prove that Landauer's limit is true. How reversible computing reduces energy consumption? Okay, so now we have NAND gate, NOR gate. So our entire chip is our transistor, everything is made as a gate. So we are doing gate based computer only. So we have AND gate, OR gate, everything. So AND gate, for example, AND gate has two input and one output. Okay, so here information is lost there. So because if I know the output, I cannot bring the input. So that is what irreversible. And reversible, if you know the output, you can bring the input also. So Charles H. Bennett, he told, IBM scientist, he told that if you avoid this, if you avoid if the okay, if you avoid the irreversible things, if you make all the reversible gates, then energy dissipation problem can be avoided. Erasing one bit of information dissipate at least kt logarithm of n joules of heat. That is 2.85 into 10 power minus 21 joules at room temperature. Okay. So K is a Boltzmann constant. So it's 1.380 into 10 power minus 23 joules per Kelvin. And T is the temperature in Kelvin, that is 300 in room temperature. And logarithm of 2 is point. So if you just multiply it, you are getting this value, 2.85 into 10 power minus 2 joules. Okay. Since no in reversible computer, so that we will see later, no bit is erased. If you are not erasing any bit, then this energy can be saved. Okay. Okay, so entropy is the main topic for the future computing. So in future computing, we have to measure what is the entropy, everything. Okay, so we are just going smaller, smaller. Okay, our transistor are getting smaller in size and faster and denser. Okay, in the same area, we are packing more number of transistors, and thermodynamic limits also important. That means, so if you pack densely, then heat also will be more, because leakage current is also adding. So shrinking also adding to the heat. Shrinking also adding to the heat, because if you shrink more, then the leaking current is more. That also produces heat, because there is no information stored, there is no information erased. Information storing and erasing, it generates heat. That is another heat. But this leakage also is another heat. Okay, we must preserve information, reduce entropy, increase. Erase information means entropy will increase, then heat generation. So the logic is we should not erase any information in the reversible computing. But in irreversible computing, we are erasing it and we are storing it. Okay, so reversible computing, no information erasure, so entropy is just maintained and it is constant. In quantum computing, by nature, the quantum gates are reversible. By nature only it is reversible, but the measurement is not reversible. Measurement is irreversible operation. Once you measure, okay, you cannot generate the quantum state. So quantum state collapsed. Okay, so measurement is irreversible operation, but the quantum gates all are unitary gates, so all are, it's a reversible operation. So energy efficient computing means it should have minimum entropy. Okay, it should not produce more entropy. Okay, so Landauer's limit we have seen, but right now what is the heat? So right now we are 1,000 times above the Landauer's limit. So now we no need to bother about Landauer's limit. So Landauer's, how to reduce the Landauer's limit, we don't want to discuss now, because we are already using 1,000 times. Already we are wasting 1,000 times the Landauer's limit. So Landauer's limit is a minimum wastage. Okay, the KT logarithm of n, that is the minimum heat you cannot avoid. But our heat we are generating is 1,000 times more than the Landauer limit. Okay, Taiwan's semiconductor manufacturing company, they are producing 5 nanometer to now 2 nanometer also. Switching energy is 1,000 times of Landauer's limit. Gap between theoretical and actual limit is very high. Okay, this shows how complementary metal oxide semiconductor CMOS technology. So lot of changes has to be done in CMOS technology itself, because already we are 1,000 times above this Landauer limit. So we have to go below the Landauer's limit. That was our target, but already we are above. Okay, so a lot of things has to be changing in the CMOS technology itself. We have to change a lot of things, even with extreme miniaturization. Okay, so now 2 nanometer and tightly packing electronics still waste lot of energy because of leaking. Okay, okay, then why break the Landauer's limit? Even, okay, so Landauer's limit, even if you now think about reducing the even breaking the Landauer's limit, so it is good for future, because we have to have a lot of AI application, we have a lot of HPC application. We can go for 3D stacking of the stick, so in the same area we can pack one above the other. So those things will not be possible if you are not reducing below the Landauer's limit. So enable ultra low power chip, battery life will be skyrockets. So once you charge, you no need to charge for next 2 years if we achieve this reversible computing, because it is not going to take much power. So one charge it will go for 2 years also. So essential for AI, HPC, mobile, and 3D stacking. So we have to at least go near this Landauer's limit to achieve these things. Reduce cooling and energy cost. Okay, so it's not only energy is wasted as a heat. Okay, energy is wasted as a heat. That heat also you have to cool it. So you are using AC also for servers. Okay, for data centers. So you are using air conditioning system, that also you are wasting power. So how much power is wasted? So 80% of the power is wasted as a heat from the chip itself. And to cool that heat, again you need ACs to cool that. Okay, if you go for reversible computing, only 20% of the energy will be used and no need for any cooling. That situation also may come. And for wearable devices, and for portable devices, so battery life will increase. Okay. So Richard Feynman's insight is no energy needed if no information is lost. That was his conclusion. Okay. So if no energy if no information is lost, then there is no need for energy. So reversible operation have no theoretical minimum energy, only erasure data loss energy. Okay. The Bennett reversible computing. So after this, Bennett is a student of Feynman. He told compute, copy, and uncompute. You follow this strategy he is telling. So don't erase anything, compute, you copy the result. Okay, your end result you copy and you do uncompute. Don't erase it. So in that way you can achieve reversible computing. Okay, so he told if reversible computing is there, no energy is needed, but he told how to do the reversible computing. So removes need to store all intermediate information. That means so you have to delete all the temporary files. Deleting means again erasing. So you should do uncompute, not deleting or reverse. Okay. Uncompute is reversible computing. Avoid entropy, so avoid heat. So if you avoid entropy increase, you can avoid heat. So how you are doing uncompute? So that I have another slide also. So resetting ancilla bits via uncompute is reversible because you store them to restore them to zero using the inverse of computation that create them. So that means initially you are setting the qubits to zero. Okay. So if you come reverse in the circuit, then again it is going to zero only. So we are not erasing any information. That is what called uncompute. Okay. So I have two inputs. I know the output, but I cannot know the input. Input can be 2 plus 2, 1 plus 3, or 0 plus 4, or 5 plus minus 1. So there are lots of n number of possibilities are there. So this is irreversible computing. From output, I cannot generate the input. So whatever the input I given, it is lost. It is erased. So that energy is lost as a heat. So what is reversible computing? Here, for example, if you see, we have two inputs, x and y. So I can have x plus y in one output, x minus y and output. So if I know x plus y and x minus y, I can generate the x and y. Okay. So this is reversible computing. So what is the main difference in reversible computing? The number of inputs and number of outputs should be same. Whether you require or not, it does not matter. If you don't require also, you should have dummy input and dummy output to match one-to-one mapping. Okay, that was the first rule to make the reversible computing. Okay. So to make the reversible computing, the number of input and number of output should be same. The output uniquely determines the input and no information is lost during the process. So this is actually essential in the quantum computing where all operations must be unitary and hence reversible. So in quantum, all the operations are unitary matrix. Okay. Whatever gate you apply, it's all unitary matrix. Okay. Hadamard gate, whatever gate, XR gate, Tifoli gate, whatever gate you apply, all are unitary matrix. So it is reversible. Okay. So why computer use energy? Because we are using AND gate, OR gate, NOT gate. Those gates are irreversible operation. Okay, you cannot get back the input from the output. So since those gates are irreversible, so computer uses energy. Otherwise, computer does not need energy. Erasing information consumes energy. One bit erasure dissipates kT logarithm of 2 joules of heat. So in modern microprocessor, since it is tightly packed, so more energy is lost as heat. Miniaturization worsen the issue. That means if you go 2 nanometer scale, so definitely it is leakage current, thermal limits, transistor shrinking. So all this creates problem. Low power computing is growing need. Okay, this is a future need for mobile device, large scale data center for that. Okay, because we need to use low energy because electricity, if as much as electricity you are using, it is not good for environment. Okay, we are producing so much CO2 that is not good for environment and our requirement is also growing, so we should think for alternate approach to reduce the energy. Okay, so here actually we have to change everything from bottom to top, from physical to algorithm. So physical implementation, whatever now we are doing, that has to change to adapt to the reversible computation. Gate, whatever gate we are using, that has to be a reversible gates. Architecture has to change, machine code has to change, high level language has to change, algorithm also has to change for the reversible computing. Okay, so right now we are having irreversible classical computer. Okay, so now we are discussing about reversible classical computer, and then quantum is by nature it is reversible. Okay, so there are three things. Right now we are discussing irreversible. Right now we are using irreversible classical computer. So we are discussing reversible classical computer. Okay, and in future quantum computer. Quantum computer by nature it is reversible because all the gates are unitary operations. Okay, so these things mainly we are discussing about reversible classical computer. Okay, so physical implementation, gate implementation, these things are classical reversible computer. Okay, so our requirements are increasing. AI exponential growth is driving demand for more powerful chip architecture, because now if you see Nvidia GPU things, so Nvidia A100, H100, so it's keep on every 2 months you are getting new products. Okay, Nvidia DGX box, DGX H100, DGX B300, NV72. So many things are coming up, and now Nvidia came up with their own CPU, ARM-based CPU, it's a Grasshopper. Okay, Grace Grace architecture. So many things are coming up because we have that much demand. Okay, so we have to. So it is now AI in the initial stage. So a lot of models has to be developed, and generative AI. Many things are coming up in AI itself. So huge demand is there for computation. If there is a huge demand for computation, how we are getting computation? We have to give the electricity, so there will be a lot of loss. Okay, so energy is the bottleneck in traditional computing. And then heating. Okay, so you have to cool. So cooling also, earlier we used normal AC, then precision AC, then rear door heat exchanger, then now we are removing the heat sink and putting some equipment which takes water or some coolant inside. That is a liquid cooling system. Okay, direct to chip liquid cooling, DCLC. So all these things are coming up to cool, because that much heat is generated. If you are not extracting that heat, okay, then the chip will burn, or it will go for throttling. What is throttling? Anybody can tell? What is CPU throttling? What is CPU throttling? Okay, so how can we generate qubit? Okay, so qubit can be generated by multiple ways. Okay, so qubit is nothing but some quantum particle. So quantum particle which is 10 power minus 9 to 10 power minus 15. The particle which are of the size 10, from 10 power minus 9 to 10 power minus 15, those are called small particles or quantum particles. Okay, so what are those particles? Electron, neutron, proton, photon. Okay, those particles are the quantum particles. So that is your quantum particle. Okay, you are manipulating the quantum particle. So the quantum particles is the qubits. Okay, so you can make qubits with superconducting qubits, trapped ion, laser, that is optics, photon based. So many methods are there. Okay, energy and entropy relation. So if the information, okay, if more information is there, for example, if you know about one person more, that means you have more information about that person, so your relationship will be good. That means your entropy is disorderness, so disorderness will be less. So you can understand the person very easily if you know more about his, what he likes, what food he likes, what color he likes. Okay, so if you know more information about that person, automatically the entropy will decrease. So that is, and if entropy decreases, energy wastage decreases. Okay, if I understood some person very good, okay, if I ask some work, he will do immediately. If I don't understood that person, I will be asking the work, he will not do that work, so my energy is wasted. Okay, so that is a relationship between entropy, energy, and information. Okay, what is denser computing? Denser computing, we are packing more and more transistor in the same die area, chip area. Okay, so then leakage current is there, then heat dissipation is there. Since there are more components, okay, if the heat is not removed in the right time, then it will damage the circuit itself. Okay. Okay, noisy intermediate scale quantum, NISQ era. So right now we are in the NISQ era only. So the future will be fully fault tolerant quantum computing. That means there won't be any fault. But now, see, since we are playing with the subatomic particles, atom, electrons, subatomic particles, their position and momentum cannot be measured at the simultaneously. Okay, so when you measure the position, you will not able to measure the momentum. If you measure the momentum, you will not able to measure the position. So always there is a uncertainty. Okay, always there is an uncertainty. So we are in the noisy intermediate scale quantum, so that outside the atmosphere everything is affecting, and the qubit has more noise in it. So the qubit with more noise is called noisy intermediate scale quantum. If the qubit, perfect qubit, if you get perfect qubit, then it is called fault tolerant quantum computing era. So that means now we are having 10 power minus 3 error. Okay, we are in the 10 power minus 3 error. Classical computer, we are in 10 power minus 12 error. That means for 10 power 12 operations, so one error will come. But in now, for 10 power 3, that is 1000, for 1000 operation we are getting one error. That is noisy intermediate scale quantum. If you can improve it, okay, if you can improve it to 10 power minus 6, that is 10 followed by 6 digits. So yeah, so 6 is 10 lakhs. For 10 lakh operation, if you get one error, that is 10 power minus 6 error rate. Okay, so if you achieve that, that is fault full, at least fault tolerant. Okay, but classical, we are now in 10 power minus 12. That's why error rate is very very less. Okay, yeah, we are now in the NISQ era only. So our error rate is 10 power minus 3. People are working with so much error correction codes. And so with noisy qubits only, with some error correction code, you can achieve some results. But if qubit quality increases, then the less error correction codes are needed. Yeah, in future we may get perfect qubits. But right now, all the qubits, whatever we are having is NISQ, noise intermediate scale quantum. Yeah, this Eagle, many IBM actually they are naming all their processor in the bird's name only. So lot of Sycamore, many processors are there. IBM, Intel, sorry, IBM, Microsoft. They are releasing lot of processors. Okay, okay. I think so. Energy bottleneck is there. Okay, what is adiabatic computing and energy recovery? So we are using energy in that 20% of the energy is used for the actual work and 80% is dissipating as a heat. Okay, that is our main concern. Okay, now how it is dissipated as a heat? So if you want to ground it, it will dissipate. So instead of grounding it, remaining energy, you store it in a capacitor and reuse it. That is the technique called adiabatic computing. Slow charge capacitor will be used, reduce dissipation. So energy to heat, that conversion it is reducing, and the energy is stored in the capacitor, and that energy is given to LC. Okay, induction capacitance resonator, LC resonator. Okay, allow energy to oscillate instead of dissipate. So instead of dissipating as a heat, the energy will go front and back. Okay, oscillate. It will oscillate and it will activate some chip, and with that energy you can do some useful work. That is called adiabatic computing. Okay, so resonant logic, recycling energy, logic gates connected to resonators, energy bounce back to components and losses remains. So, but still losses are there because of defect, imperfection. Okay, because semiconductor doping is there, parasites. So all these things take some little energy, but most of the energy is saved. For example, now 80% is wasted, but if you use this LC resonator and capacitor, these things. So that energy can come back, so that your loss will be 40% or something. That is also good gain only. That is called adiabatic computing. A lot of work is going on in adiabatic computing also. So reversible computing and energy recovery. So reversible, if you reverse the computing, that is decomputing. What is reversible computing? Is decomputing. Okay, you are not erasing it. You are decomputing. You are from input to output. For example, in gate operation, you are traveling. Okay, you are traversing from input to the output, and finally you are measuring it. Okay, measurement is a irreversible operation. Okay, so you are measuring it. So before, so you just copy the result. That means through some gate, and then you come back from output to the input. That is called decomputing. Energy, what is adiabatic computing? Energy stored on capacitor is recycled rather than lost. Okay, so adiabatic computing. So these things, if it is materialized, then it will be very useful for HPC and other AI tasks. Okay. So double computation for the same energy. Early design shows, so same energy you can do 2 times computation, or you can use half energy and do the same computation. Okay. So what are the challenges in energy recovering chips? So building reversible logic gate itself challenge. Okay, then we have to build high quality resonators. Okay, high quality resonator, so that resonator should not leak some energy. Okay, and integration into CMOS process. These are some of the challenges now. Okay, and then dark silicon. How many of you know about dark silicon? So for example, in a GPU chip, okay, you have some 1 lakh transistors. All 1 lakh transistors are not active simultaneously. Only 10 to 20% of the transistors are active. Why? Because when we reach 10 to 20% only, the heat is enormous, and dissipating and releasing that heat is very challenging. So if you activate all the silicon, all the transistor, then chip will burn. So that is, so remaining 80% of the chip is not used, not utilized. The remaining transistors are not utilized. That is called dark silicon. Okay, so heat is not the limiting. Okay, sorry, area is not limiting, but heat is a limiting. Okay, heat, not area, limiting performance. Heat prevents full utilization of the silicon area. Reversible logic solve thermal density problem. So if you do reversible logic, so you can save density also. So future directions. So silicon. So silicon photonics. So light, actually light does not have any mass. Photon does not have mass. So photon will not create heat. So mostly they are focusing on moving towards silicon photonics for this reversible computing. Quantum computers are logically reversible but demand huge energy for refrigeration. So quantum computing, by logic it is reversible only. Okay, so all based on unitary gates. But to make quantum computer, you need a cryogenic refrigerator that will consume more energy. Okay, so here we are just considering the difference between the classical reversible computer and quantum reversible computer. Okay, so classical reversible computer, if you make all the gates reversible, and if you make a resonator, okay, LC resonator, then the excess energy will be stored in the resonator, and it will be reused for the computation. So that is one thing, that is perfect. But for quantum, by nature it is reversible, everything is fine. But to make the qubit, okay, stable, for superconducting qubit example, we need cryogenic cooling. That cryogenic cooling will take more current. Okay, so in terms of power, classical reversible computing is much better than the quantum reversible computer. But parallelism, if you do quantum parallelism, quantum, if you want to solve some very great challenges, NP hard problems, then there is no other way, we have to come for quantum only. Okay, reduce cooling load, scalable without reducing nuclear load. So yeah, so reversible Boolean operations. So these are all some of the reversible NOT gate, Feynman gate. Feynman gate is nothing but XR gate. I think you have studied the gates. Fredkin gate, swap gate, Toffoli gate, Parrish gates. These are some of the reversible Boolean gates. Okay. So these are some of the conditions. So first, reversible gate should have n number of input and n number of outputs. So it should be one to one mapping. So if it is three input, output should be three. Okay. If it is two, output should be two. So that is the main reason. Okay. Because in classical for AND gate we have two input and only one output. So number of input and number of output is not same. But in reversible it should be same. Okay. So direct fan out is not allowed in the synthesis of reversible circuit because one to many concept is not reversible. So one to many, one output you cannot connect to multiple input. That is fan out. Okay. So from one circuit you are getting one output. That output, how many input you can connect? That is the fan out. Direct fan out is not allowed in quantum or reversible logic. Okay. Fan out however is achieved, but fan out is needed because that output you have to give to some other input is achieved using the additional gates in reversible circuit. There is a different way. There is a trick. Okay, so they are approach is different and they are getting the same functionality, but with a different approach. So number of reversible gates. Okay, so number of reversible gates used in the circuit, that is n, and constant number of input Ci. And if for example, okay, I have two input but I need only one output, why I should have two output? Whether you need or not, to match the first condition, one to one mapping, you need to have dummy outputs. Okay, if you don't need input also, you should have dummy inputs. That is a garbage output and garbage input. And then quantum cost is how much primitive gates, how many primitive gates you are using in that circuit. That is called quantum cost. Okay. Any doubt in this? Can we define any storage of energy from lightning strike through adiabatic computing? Uh, I don't know this one, lightning strike things. Adiabatic is actually energy is stored in the capacitor and it is used back. Uh, Maybe in future, but that actually adiabatic computing, actually we are dealing with the energy within the circuit only. But this lightning things are coming from outside the circuit. So adiabatic computing actually computing. So we are already giving the current to the computer and it is passes through the circuits. And instead of grounding that remaining energy, we are capturing it in the capacitor, and that energy stored in the capacitor is used to again feed the circuit. Okay. Green hydrogen production system with the electrolysis using quantum computing. We can do simulations. So we cannot do in quantum computer we cannot do any hydrogen or anything. See, so we can do computation only. For example, if you want to know, okay, so if you want to know, if you want to do some experiment, okay, so you have to do your first observation, then you have to do hypothesis, then you have to do computation, then experiment. Okay. So here the number of experiment cycle will reduce. So you can do all the computation and you can find, okay, if I mix this element with this element, you will get this element. So instead of doing it, if you do it, you have to do multiple times. You have to do lot of repetition. Okay, you have to do lot of prototype, or you have to waste lot of equipments, raw materials. Okay, that you are reducing with computation. So basically it is a computation simulation. We are simulating it. Okay, we are not doing actually. So we need HPC for simulating this kind of experiments. Okay, we are doing like a video game, we are doing simulation. Okay, instead of doing it physically, we are doing simulation. When we are getting near result, okay, some near result, we are then that method only we will try in the experiment, so that the number of iteration getting reduced. But HPCs also there is a lot of limitations. That's why we are going for quantum computing. So in quantum computing we will simulate this, then when we get the right result in the simulation, then we will do it in the physically. Okay, so quantum computer cannot do anything. Quantum computer can do simulation only. It cannot generate. It can give, for example, you have thousands possibilities. Okay, in that thousand possibilities, all thousand you have to check, and there will be two useful process you will get. So then if you do 1000 in HPC, it will take more time. If you do 1000 in experiment, you have to waste lot of resource. So computation you have to do in quantum computer. It will tell the right process. Okay, out of the 1000 process, okay, this 599 process is the right process, so I will do 599 number. That process only I will do as a experiment. So my experiment cost will reduce. Okay. Okay, primitive gates are the basic gates. Yeah, X gate, Z gate, H gate. Yeah, these are all the primitive gates. Not Pauli X gate, Pauli Y gate, Pauli Z gate, Hadamard gate, C naught gate. These are all the primitive gates. No, primitive gates are all useful only. See, all the single qubit gate, 2 qubit gate, 3 qubit gate, 4 qubit gates are also there, but we are not going to implement 4 qubit gates directly. That 4 qubit gates will be decomposed into several primitive gates. Actually, in the quantum computer, only primitive gates are implemented. Okay, so primitive gates are very, very useful. Without primitive gate, nothing is possible. So actual implementation happens in the primitive gates only. For example, in our classical computer we are having AND gate, OR gate, XOR gate, NOT gate, but everything is there. But are we using everything? We have universal logic gate, that is NAND gate, NOR gate. You can achieve AND gate operation using NAND gate. So like that, one universal gate will be there, one or two universal gates will be there. With that only it will be made. Okay, we are not going to use all the gates. Any reference book for simulation on HPC for reducing iteration and implementing height? There is, actually, there are a lot of softwares. So, molecular dynamics, quantum chemistry, okay, WASP, lot of softwares are there. That softwares you can install and you can write the input file and you can do calculation and you can get the output file and you can analyze it. So, so there are a lot of softwares available for quantum chemistry, molecular dynamics chemistry, everything. Okay, and for material science also, lot of softwares are like that. For computation, like for example, MATLAB you can do. Okay, like quantum espresso, some software is for material things as there. WASP is there, Gaussian is there, Gromax is there. A lot of computation softwares are there that you can use either in HPC or servers, and you can simulate it. So, say green hydrogen, there is no particular software because see everything finally everything is reduced to atom. Hydrogen is for two atom. So everything reduced to atom. So if you add more atoms, it become a different molecule. So atomic scale simulation, whatever atomic scale simulation softwares are there, you can use those things. Universal gate, C naught gate is universal gate. The Foley is CC dot gate. That is also universal gate. Pauli X gate, rotation gate. These are some of the universal gates. Okay. Why we need reversible system? We said to reduce heat and increase computation power. Yeah, because now our most of the power is wasted as heat. Okay, so there is a law of conservation. Energy can neither be created nor be destroyed. It can transform from one form to another form. That means, so your energy is wasted as if some heat is coming means heat is also energy. So electric energy is converted to heat. That means some part of electric energy is going as a heat means it is not doing any useful work. So that we have to arrest it with a reversible logic. Yeah, quantum computer by nature it is reversible logic, so it is not going to lose any energy during computation, but most of the energy is used for cooling. Okay, the cryogenic setup. Yeah, QC circuit, it is not taking more energy. Quantum circuit, it will not take more energy, but to make qubit stable, so the cryogenic setup, it will take more energy. Okay. Yeah. So this is the example of fan in, fan out. So fan in for gate is just some basic examples. So three input and one fan in is three. So here fan in is five. That means here this one output powers 4 input, that is fan out is 4. Okay, but direct fan out, why we are telling fan out here? Direct fan out in reversible logic is not allowed. Okay, there is another method, directly we cannot do it, because directly if you do, then it will become 1 to 4 mapping. It is not 1 to 1 mapping. It's not 1 to 1 mapping. So to be a reversible logic, it should be always be 1 to 1 mapping. Okay, so direct fan out is not allowed in reversible logic. So number of inputs and number of output will always should be same. That is the first principle. Then quantum cost, number of quantum primitive gates required to implement it. So primitive gate is very much needed. Okay. Fan out indicates that direct fan out is not allowed. Duplication needs special handling. So we need to handle fan outs in some special way. That I will discuss in the next slides. Garbage output. So number of output and number of input should be same. So we have to add garbage input, garbage output. So garbage input called ancilla bit. Okay, ancilla bit output is garbage output. Gate delay, time to execute based on the basic gate operation. No fan out and no bit erasure. So since no fan out, so no erasure is there. Primitive gates are C naught gate, NOT gate, Adamar gate, Toffoli gate. These are all some of the primitive gates. Okay. So this is V gate, V dagger gate. V gate is square root of Pauli X gate. Okay. V dagger is just inverse, Hermitius operation. Okay. Okay, so there are two types of gates, Clifford gate and non-Clifford gate. So Clifford gate, okay, so you are applying to the Pauli, you are applying some gate, okay, Clifford gate, and then Pauli matrix, Pauli operation is maintained, I mean that is called Clifford gate. If Pauli operations is not maintained, then it is non-Clifford gate. Okay, so Clifford gate is a quantum gate that maps Pauli operation to Pauli operation under conjugation. Okay, so Pauli matrix is X, Y, Z. That means only rotation operation. So if you do only rotation operation, that is Clifford gates. Okay, if the result is not Pauli operations, then it is non-Clifford gate. Okay, so if the result is again Pauli operation, then it is Clifford gate. If the result is non-Pauli, then it is non-Clifford. That does not preserve the Pauli group under conjugation. So if you reverse the output, you should get the original one. That is called Clifford. Okay, if you reverse it, if you are not getting the original, that is non-Clifford. So Clifford gate are easy and classically simulable. Okay, non-Clifford gates are hard, quantum power enabling, and require for universality. So Clifford gates are easy. Only with Clifford gate, we don't need quantum computer. We can do this all the things with classical computer itself. Okay, reversing these things we can do, conjugate. But non-Clifford gates is very difficult. Okay, that is T gate, T dagger gate, V gate, V dagger gate, Toffoli gate, and control Z gate, rotation gate, again rotation on Z axis, rotation on X axis also there. So these are all the non-Clifford gates. Okay, why it is non-Clifford gate we will tell. So if you reverse, you will not get the original. Okay, but it's reversible also. The universal set is Hadamard gate, T gate, C naught gate, or V dagger, C naught. V is root of X gate. Okay, root of X gate. So key reversible gate is NOT gate, Feynman gate. Feynman is called otherwise C naught gate, the Foley gate, Pedron gate, Paris gate. Universal set of classical reversible gate. So all quantum gates are reversible, unitary operation. Measurement is irreversible operation. So once you measure, the quantum state collapses, so you cannot regain it. Okay, so that's why it is called irreversible operation. Quantum computer naturally aligned with reversible logic. So these are some of the unitary matrices. So what is in quantum computing? Qubit is nothing but a vector. Qubit is nothing but a vector. Gate, quantum gate is nothing but a matrix. Okay, so in the qubit, you are applying matrix, that is vector matrix multiplication, and the result will be vector only. So there is a vector, okay, there is a atom in some position. Okay, there is an atom or electron in some position. You are applying some external RF pulse. That is the quantum gate. Okay, that is a matrix form. Okay, so you are multiplying matrix and vector, and you are getting another vector. That means the electron or the quantum particle move from one part to other part or rotate to another part. Okay, it went to another axis. So maybe it's momentum and velocity, it's displacement, somewhere it is changed. Okay, so result is also vector. So basically qubit is a vector, gate is a matrix. So you are applying quantum gate on the qubit, and the result is a another vector. Okay, so these are all some of the unitary matrices of different gates. Okay, so two qubit primitive gates, c naught gate, control Z gate, swap gate, I swap gate. Yeah. Any doubt in this? Can you find relationship between energy and information? Yeah. If information is more, energy loss will be less. If information is more, entropy is less, energy also less. So energy and information actually, yeah. If information is more, energy will be less. Real-time problem where quantum computing is used to solve it. Yeah, now a lot of already in the optimization things, many things are going on actually. Volkswagen, so traveler salesman problem. Okay, this transport services, they are using actually for route optimization, they are using it. For drug discovery also they are using. So where multiple, so lot of combinations are there, you have to check many things. So then parallelly in quantum computer you can check all the things. For example, if there are 1,000 routes, quantum computer can check all the 1,000 routes are simultaneously and find the best route for you. Route optimization. There's some reference book, website material, or links to refer for topic dealt in today's class. I did not get any books, but lot of research articles are there. Reversible computing, lot of research articles are there, because research reversible computing till no product has come. Okay, some 2 3 companies, very rarely some companies are working. Mostly the content what I got from is mostly from research articles only. So we don't need to choose. For example, okay, the quantum computer is already made by some companies. Okay, so they have implemented, one company implemented in one way and another company may be implementing it in another way. So they used some gates. Okay, so we will write Qiskit program only. Okay, so we will write Qiskit program, and there is a transpiler, there is a program called transpiler. Okay, so compiler, I think everybody knows. Compiler converts our high level programming language to the low level programming language. So low level language, machine language. Okay, but this is called transpiler. This converts our Qiskit circuits to the underlying hardware circuits. Okay, so because same circuit, if you transpile it in one IBM computer, it will transpile differently because to that native hardware. If you transpile in another quantum computer, it will transpile differently. So we are not choosing which gate or something. We are writing, we are whatever the basic gates are available, we are preparing the quantum circuits, and then when we are running in the actual quantum computer, the transpiler will take the job. Okay, transpiler will do the conversion. Okay, so we are not going to deal directly. I will show you how can we create a new qubit. So like a superconducting qubit, trapped ion qubits. So you are just, actually qubit is nothing but some electron. So for example, trapped ion, so you are trapping the ion inside some vacuum chamber or something. Then you are making that subatomic particle, quantum particle stable. Okay, so it should not move here and there. So making it stable. So to make it stable, you need to reduce the temperature to Kelvin level. So then it will not shake. Okay, it will not affect to the external heat or external noise. So then you are making stable, then you are applying some pulses, that is quantum gates, to the qubits, then it rotates. Calculation rotation you are doing, then that is the computation you are doing. So for creating you need subatomic particles. Okay, so that subatomic particles can come from any source. Okay, and then you have to make the subatomic particle very stable. It should not react to the atmosphere. Okay, that is what heat, that is what qubit. Okay. What are the simulation softwares? Qiskit is one of the simulation softwares. So machine learning, many I don't have much knowledge about machine learning things. But anyway, so it's a highly parallel task. See, quantum computing will do a lot of parallel tasks. So instead of doing in HPC, if you do in quantum computer, so the time it will reduce drastically. For example, even if you do, even if you take a lot of time, also sometimes some task may not complete. It will take very big time actually. So if it is instead of one day, if it takes 10 days, okay, I can adjust. If it takes 10 million years, what I will do? I cannot do with the same traditional computer. I have to go for alternate computer. That is quantum computer. Okay. Instead of one day, I can wait for 10 days. 100 days also I can wait. But if it is 10 million years, who will wait? And what is the use? So we are, so machine learning, that training, so lot of data are there. So highly parallel. Okay. Quantum computing is parallel. Okay. Reference book, yeah, mostly it is research articles, IEEE papers you can read. Okay. Because these things are evolving, so it is actually still in the research phase. So even if you get a book, it will be outdated actually. Why quantum gates requires encoding? See, because you have to encode. No, you have to encode. Then only it will go as a binary. So cryogenic cooling is required. So a lot of things are there. Control electronics is needed to give calculated RF pulse. You need control electronics. To make the qubit stable, you need entire cryogenic setup. Then RF pulse manipulating. Then lot of middleware softwares. Many things are there actually. Right now, what available to us is only Qiskit we have. Qiskit and CDAX, Universe. This kind of simulators only we have. Okay. So we are not creating qubit by logical. The qubit is physical. Qubit is nothing but subatomic particle. It is a particle. Okay. It is not a information. Qubit is particle. Okay. With its position, we are giving. Okay. If it points up, if it's magnetic is north pole, then it is treated as zero. If it's magnetic is south pole, then it is treated as one. So we are just encoding information. Okay. Yeah, yeah, I will share the articles later. Yeah, later I will share. Yeah. So three qubit primitive gates, CC not gate, Federin gates, CSWAP gate, Parish gates, so a lot of gates are there. So logic operation. So C not gate is control not CC not. So if two bits are control bits are one, then the target will be activated. That negation will be done. Otherwise, it will not be done. So like that. I think gates are covered. So here one thing we have to notice is quantum cost. So for example, you see 15 to 20 gates, primitive gates are needed. Okay. If you want to implement the Foley gate with no ancilla. Ancilla is what? Dummy input. Okay. You can consider as a dummy input to make one-to-one mapping. So without the dummy input, if you do, we need 15 to 20 gates. But with ancilla, it is reduced to 5 to 6 gates. So always we should use ancilla bit. Ancilla is the dummy inputs. Okay. So here Federin gate 45 to 60 gates without ancilla, but with ancilla it is 15 to 8. Okay, so like this is reducing. So V and V dagger gate, this is square root of X gate. Okay, square root of not gate, square root of X gate. So this is the matrix. So used in quantum circuit decomposition. So you are just writing quantum circuits with whatever the available gates, but actually in the ground level those gates are not there. Those are different gates. So you have to decompose the gates into primitive gates. Okay, decompose the fully gate requires one sampler 1 2 qubits gates, and then simpler 1 and 2 qubit gates liquid. Okay, reducing quantum cost in reversible circuit. To reduce the things you have to add ancilla qubits also. Constructing universal set with a minimum gate type. So universal say gate is needed. Okay, from the same gate you can just change the input and output. You can get AND gate operation. If you in the same gate you will get OR gate, so like that. Okay, so T gate is rotation in Z axis, pi by 4 rotation. S gate is rotation on Z gate is pi by 2. Z gate is pi, Pauli Z gate. Okay. So just we are rotating, we are displacing. So we are playing with the position of the subatomic particle. So Feynman gate is nothing but XR gate. So if control qubit is 1, then it will be negotiated. Okay. So here 2 input and 2 output. First condition is satisfied. Quantum cost for Feynman gate is 1, because 1 primitive gate is used. Fan out is not allowed in reversible logic. However, fan out in reversible circuit is achieved using additional gates. Okay. So if you want to give output to some other input, so you can put another gate and give, not directly. Okay. Feynman gate has zero garbage output. So that means both the outputs are useful. So delay is 1 unit, 1 XR operation on quantum. So not gate is a Feynman gate. Construct input as control, B is equal to input gate. Okay. So how we are constructing XR gate with Feynman gate. So this is, if you have a measure here, you will get XR operation. Okay, nothing. Great. So then double Feynman gate. Okay. So here one XR gate, here one XR gate. A to B and A to C. Okay. So this is double Feynman gate. Feynman to double Feynman gate. So here you can have 3 input, 3 output. So it satisfies the reversible logic. So it's two C naught gates. Total cost is 2. Double Feynman is used to simulate fan out with reversible and information preserving way without violating reversibility. So garbage output are context dependent. Okay, so for some operation I don't need this. That is, then this is garbage. For some operation I don't need this. Then this become garbage. For some operation I don't need this result. Okay, so that depends on the context. So only if you need copy, put A unused. Okay, so delay. So what is the delay? Everything. Okay. So how to use double Feynman gate for XR operation? So if you do this measurement, you'll get. So for example, A, B, 2 inputs, constant. C if you put always 0, then it will behave like a XR gate. Q is equal to A into B. It gives XR. Okay. So R is 0 because C is 0, so R is 0. Okay. R is A actually. So if both the inputs are different, then the output is 1. If both the inputs are same, that output is 0. That is the XR operation. So, and now here we are using double Feynman gate for copying. Okay, fan out. Direct fan out is not allowed, as I told earlier. If you want to do fan out, for example, I want to copy this A input to all the output. Here also A, here also A, here also A. Then I will put B and C 0. Then Q becomes A, R become A, P also become A. So then I'm copying this one input to 3 output. Then I can connect. For example, fan out is So direct fan out is not allowed. For example, you have one output. This output I cannot connect to multiple. This is fan out, direct fan out. Since this is not allowed, here one input, okay, we are copying it a, so here also it become a. So now I can connect to three device. So this is not fan out. That's how direct fan out is avoided here. Okay. Yeah. Any doubt in this? Double Feynman gate for XOR operation, double Feynman gate for copying. Yeah. Okay. So Toffoli gate, so three input gate, three output gate, quantum cost is 5. So implemented using C naught, T dagger, H gate. These gates are used. These are the primitive gates to construct Toffoli gate, building blocks. Okay. Direct fan out is not allowed. You can simulate fan out using extra ancillary bit. So you understood now fan out, direct fan out and indirect fan out. So garbage output, it depends on the context. Sometimes this will be garbage, sometimes this will be garbage, sometimes this will be garbage. Depends on the context only. 0 to 2 garbage will be allowed. So maximum gate delay is 2. Can be used to implement universal classical logic such as AND, NAND. So with using Toffoli gate, you can create AND gate, NAND gate, everything. Okay. Next slide I will show you clearly. So using Toffoli AND gate. Okay. So how we are creating AND gate? So here if you put 0, if C is 0, so if C is 0, okay, if C is 0, so goes as A, so B, so it will not negotiate anything. 0, so when it will go, for example, if you put 0, 0, then it is 0, 0, 0. If it is 0, 1, 0, then again it is 0, 1, 0. If it is 1, 0, 0, here also 1, 0, 0. If it is 1, 1, 0, here both are 1, so it will negotiate. So here result will be 1, 1, 1. That means if both the inputs are 1, then the output is 1. This is AND gate. So we are creating AND gate with Toffoli gate. Okay. So this is the result. For all other three operations, it is we are getting 0 only. Only for 1, 1, we are getting 1. This is how we are constructing AND gate using Toffoli gate. Okay. So now how we are getting NAND gate? If you put C equal to 1, for example, here we are putting C is equal to 0. But now instead of that, if you put C is equal to 1, then it will become NAND gate. Since circuit is not there, I'm just writing here. Okay. 0, 0, C is 1. Okay. C is 1. So here you will get 0, 0, 1. So that means 0, 0, 1. If it is 0, 1, 1, then also you are getting 0, 1, 1. When you are doing 1, 0, 1, you are getting 1 0 1. When you are doing 1 1 0 1 1 1, so here now it will negotiate this one, so it will become 1 1 0. Sorry, 1 1 0. This is the NAND gate truth table. 1 1 1 0 1 1 1 0 0 0 1 0 1 1 1 0 1 1 1 0. This is the truth table for NAND gate. Okay, this is how we are achieving. So based on our requirement, we can change the ancilla bits, okay, from 0 to 1, 1 to 0. Okay. Okay, compute, copy, and compute. So this is Toffoli gate. Okay. So here, so I am putting Toffoli gate. So this is, I am just, this qubit I am initializing to 1. So this qubit I am initializing to 1. Okay. Because I am putting 1 X gate. So this qubit is initialized to 1, 1, 0, 0, initial state. Okay. So when it goes here, so it become 1, then it will, so here you will get, okay, so Toffoli get, this is what uncompute we are doing. So here, so compute, here compute is happening. Okay, in this XR gate compute is happening. In this C naught gate, that is CC naught gate. Okay, this is CC naught, Toffoli gate, CC naught gate, control naught gate, CC naught. This is C naught. So here we are doing copy. We are copying the result to qubit 3. Okay, so compute happened, copy happened, this part is uncompute. So we are not deleting anything. So compute, copy, and compute. We are doing uncompute there. Understood? Since we need only 3 qubit, Toffoli is a 3 qubit gate. So this qubit 3, 0 to 3, qubit, fourth qubit is the ancilla qubit. Because we need to store it in the ancilla qubit, because one more qubit is needed to store the intermediate, that is result, and then you do uncompute, then again it will go to the same state, whatever state is there, it will go to the same state. Okay, so AND gate is implemented here using ancilla and Toffoli gate. So this part is a compute part, this part is a copy part, this part is a uncompute part. So ancilla qubit you are measuring, because if you measure here you cannot uncompute, because if you measure, measurement is a irreversible operation, so you should not put measurement operator on the actual qubits. In ancilla qubit you can measure it, you are getting result from the ancilla qubit only. If I put measurement here, then uncompute will not happen, because it lost its state, because it's reversible, it is not reversible, measurement is not reversible. Okay, when we reset an ancilla using uncompute, we do not erase information, we are not erasing information, so there is no loss of energy. We reverse the computation that created the ancilla, so the information flow back to the input. Compute is produce garbage, copy output, keep useful results. Uncompute, garbage return to 0. We are not cleaning the garbage, just reversing the process, so that, for example, I am using some paper and I am tearing it and throwing it dustbin, that means compute is done. Okay, but here again from the garbage I'm just making it as a white paper, that is decompute, so there is no loss of paper. Okay, but in irreversible computing, the last paper is lost. Okay, it's like rewinding. Okay, so same operation you are doing again, so it becomes reversible. So here also during computation you did Toffoli gate, during uncomputation you are using same Toffoli gate, because both are unitary matrix. So this inverse is again inverse. I will get same value. Okay, beginning value you will get. So it's a unitary matrix. That's why quantum by nature it has reversibility. Okay. Fedrin gate. So 3 input, 3 output. Quantum cost is 5. Direct fan out is not allowed. Garbage is depends on the context. Maximum gate delay is 2. Okay. This is a swap gate, controlled swap gate. If control qubit is there, then this 2 bits will be swapped. So logic gates you can find from the reference. So you can form AND gate and OR gate with Fedrin gate also you can make. Like Tifoli gate, with Fedrin gate also you can make AND gate and OR gate. Okay. So pitch gate, 3 input, 3 output gate, quantum cost is 4. So in this gate, advantage is quantum cost is 4. In other gates, quantum cost is 5. Okay. In Fedrin gate and all, quantum cost is 5. So pitch gate, quantum cost is 4. No direct fan out, garbage output, delay is 2, the fully based. So here, if you do with the Pierce gate, so your quantum cost is reducing. That is the only advantage. So here also you can do AND gate, OR gate, everything. Okay. Future architecture, how it will be? So we have to focus more on the existing CMOS logic and we have to convert those CMOS logics into reversible logic. Okay. Otherwise, cryogenic reversible logic, because cryogenic reversible logic for electronics, for quantum computing, there is that is called cryogenic electronics, because it's not only qubits. Okay, above little above temperature, our electronics will not also function in that low level temperature. So we have to create a lot of cryogenic electronics that also should be reversible logic. Okay, then photonic reversible computing. So light, then 3D chip stacking, because 3D chip stacking. So one chip on top of the other chip, so that in the limited area you can have more number of transistors. That is only possible if heat dissipation is very less. If you want to make heat dissipation very less, it should follow the reversible logic. Photon generates little heat. Potential platform for reversible optic logic. So challenges, nonlinear materials and integration. Okay. So this is how we are building half adder circuits in Qiskit and then full adder circuit in the Qiskit. So this is how the transpiler will do. Okay. Whatever circuit you are doing, this will not go as it is. This will go because I ran in some other quantum computer. So here it transpiled in this logic. Okay. If you do in different quantum computer, it may use different preliminary gates. So rotation, again z axis rotation gate, root x, that is V gate, rotation, C naught gate, root x, rotation gate, error correction gate. Okay, rotation gate, root x gate. So only basic gates are used in the transpiler, and then actual quantum computer uses these gates only. Okay. Otherwise our quantum circuit will be very complicated, because whatever we are doing like this, it is transpiling to this level. Okay. So gate decomposition for reversible quantum gates. Reversible quantum gate can offer decomposition into simpler simpler gates like C naught gate, H gate, T gate, Pauli gates. Okay, so decomposition. So Toffoli gate decomposed into 6 C naught gates, 7 T and T dagger gate, 2 Hadamard gate and 1 Yas gate. Fedrin gate, 2 C naught gate, 1 Tifoli gate. PS gates, Tifoli gate. So like this. So it decompose. Okay. So superconducting qubits, IBM-Q, Rigidi, they are using superconducting qubits. Josephson junction is the main component in the qubit. Transmon qubit, they are called transmon qubits. Shunt capacitor is used there. So these are some of the components used in that qubit. Okay, cryogenic refrigerations, everything. So this is how the transmon qubit is formed. Okay, so capacitor, inductor. So basically three elements only: induction, capacitor, voltage. LC resonators. So first we have to prepare the qubit. That depends on the platform. Either it can be a superconducting qubit or trapped ion qubit or photonics based qubit. And gate control electronics, we have to do control electronics, microwave, RF pulse, because these are all the quantum gates. When we are applying the force, that is the gate operation, okay, to the qubit. Then, so this is qubit, this is the quantum gate, this is measurement, okay, how single photon detectors read out electronics. So because you have to do, you have to see the result, no? So you have to measure it. Then, and some of the electronics will operate in the cryogenic, because you are keeping the qubit in the cryogenic part, and the operation in the dilution refrigerator, three parts are there. So first part will be like hot, like sun. The down part will be like earth. So that much temperature variation is there in the cryogenic electronics, which is used for the quantum computer. So our electronics should operate in different temperatures. So normal room temperature existing electronics will work. So if you want to have some control electronics for the quantum computer, that should work at least in the lesser temperature, okay. High stability power supply control system. So opportunity for, so a lot of opportunity for resonator building in the circuit, adiabatic drivers, reversible ALUs creation, software, reversible language compiler algorithms. So entire stack has to be changed. That's why it's very challenging task. So any questions? Do we pass classical information to no, everything has to be encoded into quantum information. Classical information qubit cannot understand. Qubit it should be quantum information only. To avoid direct fan out, do you always need to apply DGP, or can we use other gates also? We can use other gates also. That is just one example I showed. So depends on your context. We can use any gates. Where and when do we use these gates in simulation, sir? In Qiskit, how you are writing, you are making Qiskit circuits. Huh? Qiskit circuits, it's full of gates only. Gates applied on the qubits. See, quantum circuit is nothing but you are initializing the gate, initializing the qubits. First operation is initializing the qubit, then applying gate, then measurement. Cost is number of primitive gates used. That is the cost, quantum cost. Classical gates, the number of inputs and number of outputs are not same. Okay. So, for example, if AND gate, so we have computers. Okay, we are connecting power supply to the SMPS, switch mode power supply. Okay, and that SMPS is creating lot of cables are there, Molex connectors. So it creates plus 3, minus 3, plus 12, minus 12, plus 5, minus 5 voltages in different wires. Yellow color wire, blue color wire, black color wire. So, and that wires we are connecting as a power supply to the components. Okay, so and then it is, for example, AND gate takes two input. That means, let just example, one input is 5 volt, another input is 5 volt, and AND gate's output is output only. So that means I am giving two 5 volt, I am getting one 5 volt. What about the remaining 5 volt? The remaining 5 volt goes as a heat, but that it is not happening here. If you want to preserve also, you can, if you want to with some mechanism, if you want to preserve also, you can preserve that remaining 5 volt only. That 5 volt is gone already, it is dissipated as a heat. So if the number of inputs and number of outputs are constant, then you can save that. Okay, otherwise it is not possible. Our classical things, the number of input and number of output is not same. How you identify graphically which gate these are on circuit diagram? Okay. No, no, no. All gates are not same. So, for example, here you see this is X gate, Pauli X gate. This is also Pauli X gate. This is CC not gate. Two dots are there, na? Control, control, not. This is CC not gate. CC not gate is called Tifoli gate. This is also CC not gate. Control, control, target. This is called CC not gate. This is called C not gate. Control, target. C not gate. So this is measurement gate. So once you practice, you can easily identify. No issue. See, cost of the circuit is, see, quantum cost. This refers to the cost of the circuit in terms of primitive gates. It is calculated number of primitive reversible logic gates required to realize the circuit. That is the quantum cost. So how many primitive gates you are using to realize the circuit? That is the quantum cost. So you have to count. By counting only, we are finding the cost. Okay, Hamiltonian. Hamiltonian is total energy, kinetic energy plus potential energy. Okay. I think that is full of physics. I am not an expert in that. So Hamiltonian, what I understood, Hamiltonian is a complete energy. So it's kinetic plus potential energy. So you have to find the total energy. Okay, all the system. So some problem we need to find the lowest energy. Some problem we need to find the highest energy. So, but this is mostly physics. I don't understand much. Yeah. So, measurement means exactly what operation is getting measured inside. Let's we took product with unitary matrix like this. What happens with the measurement? Measurement is readout circuit. For example, you are using a detector. Okay, so you are detecting. Okay, so you are applying some gate. Okay, so that particular things how it is. So that is also one operation. So measurement operator, that is also an operator. For example, in photonics, it can be a it can be a detectors, single photon detectors. So while detecting it, what is this position, whether it is in the up state or down state, what is its magnetic field. So if it is up spin, down spin, so that is all the measurement. So once you measure the qubit, you know, okay, the qubit, when I measure, the qubit is in the up spin. When I measure, it is in the down spin. So based on that, up spin means you are measuring one, down spin means you are measuring zero. That is measurement. But you are measuring na, that means you are also applying some energy to that qubit is nothing but quantum particle. That means you are measuring, after that this energy also absorbed and then qubit will collapse. That means it will go to another state that is irrelevant of the computation. That is measurement. Okay. For regular software development, it is not needed. See, quantum computer is not going to replace our classical computer. Wherever classical computer struggles, for example, weather prediction, lot of parameters in AI, okay, there only we are going to use quantum computer. For normal things, it is not going to. Normal software development will be normal software development only. That will be there. Yeah. Thank you. Yeah. So yeah, I'm done with. So if any queries, you can address it. So basically, it's a reversible thing. Actually, now it is needed because now we are highly depends on this AI and other things, simulation. So definitely, power is the main thing. Now, data center actually heat is the big problem. How to dissipate the heat, and then people are thinking why the heat is coming. That's why Landauer's principle is coming. So erasing, we are always doing some, we are writing something and erasing. So I am, for example, I am using whiteboard, so I am just writing something and erasing. So he's what Landauer's principle is telling, writing, it's not taking much energy, but erasing costs you energy. Every bit erasure actually it takes energy. So kt logarithm of 2, kt logarithm of 2 is 10 power 2.8 into 10 power minus 21 joules. That much heat minimum it will dissipate. Whatever you do, you cannot reduce that, he is telling. But that also possible if you do reversible. But now without reversible also we are 1,000 times ahead of that land hours limit. We are actually using more power in the heat only. And we have chips, okay, we have transistors. We are not able to activate all the transistors because of the heat problem only. So that become dark silicon has been generated. So we have transistor but we are not able to use it. We are using only 20% of the transistor, because remaining 80% if you use it, the chip will burn. Now this is just simulation. In the software just we are simulating. Actual qubit we are not doing. Whenever whatever simulation you do, it is just we are just simulating it. We are just simulating its behavior only, but nothing quantum. When you are doing in laptop, nothing quantum. When you submit the circuit to the IBM quantum computer through cloud, then only it runs in the IBM quantum computer. Because here in simulation and all, you are not considering the noise level. For different quantum computer, the noise level will be different. There will be different types of noise are there. So you can simulate noise also here. In the simulator you can simulate noise as well. But otherwise it is a ideal, it's a fully logical simulator will give ideal result. But actual quantum computer will not give the same result as you got in simulator. But the problem with simulation is you cannot simulate more than 40 qubits in any big servers also. Because the number of quantum states increases. Okay, 2 power 40. So 2 power 40, the very big value. 2 power 32 is 32 GB. Then 2 power 33 is 64 GB. 34 is 128 GB. So if you go like this, you cannot fit the quantum state vector in the memory. Okay, so even above 50 also it's not possible. If you have multiple servers connected as a high performance computer, if you have MPI process parallelism, then also, so you cannot compute more than 50 qubits. You cannot do simulation. Real world application need a minimum 100 qubits. So none of the simulation can do real world applications. That's why we, otherwise we can simulate it, na? Why we need quantum computer? We can do everything with our classical computer only, with Qiskit program, CUDA Q or whatever it is. So we cannot even simulate. For simulation also we need quantum computer only, beyond 100 qubits. Yeah. Okay. Okay. So then, so Pilli sir is there?
Yeah. Thank you so much, sir. Jennifer is not here. He is busy in the other conference.
Okay. So I will disconnect from this.
Okay. Thank you so much, sir, for this wonderful
So
session. And
thank you for all.
thank you all the participants who have joined. And yeah, we will meet again tomorrow at same time, which is 3 o'clock. So yeah, thank you so much. And thank you so much, sir.